Today we're going to do some data analysis using Google Sheets. We're going to take some Pendulum data, and with that we're going to do some trend lines. We'll put some error bars on, do a curve of best fit. We'll do some linearization of data, draw maximum and minimum slope lines. We'll use the linear estimate test in order to find out the uncertainty in the slope and the uncertainty in the y-intercept. So lots of good stuff to do today. So what we've got here is some Pendulum data. You might be asked to collect this data yourself, but here's some ready-made stuff. We've got these increments in the independent variable, the length of the pendulum, and then at each length, 3 time measurements were made. So there was a length measured from that point of support to the center of mass of the pendulum bob. And then the time for 5 to-fro motions, there and back, was recorded. So that time that we record is going to be 5 times the period of the pendulum. So the first thing we'd like to do is figure out the average time over those 3 trials. And we can do that really quickly with a formula. Use an equal sign first to start a formula. In this case, we want to do an average. They're already giving us an average, A3 to D3, but we really want B3 to D3. So we'd like these 3 numbers here, B3 to D3. We don't want to include that number in the first column. Press enter. 3.18 is what we get here. We can then go to that bottom right hand corner and drag down, and you'll get the calculation done for all of your data. Something that we might want to do here is adjust the number of decimal places for our data. So for instance, the length here has an uncertainty of 0.1. So we should have numbers here that go to the first decimal place. So if I highlight those numbers, I can bring those out to 1 more decimal place. All of these numbers should be to 2 decimal places. We see that 9.6 isn't. That's 3. We can come back 1. And these numbers are right. They're to 2 decimal places. Now it's the period that we're really interested in this experiment. So what we've got to do is take these average for 5 periods and divide that number by 5. So once again, formula works well. Start with an equal sign. Click on the box where the number is. Divide that number by 5. Press enter and then pull down. We also need the uncertainty in the period. So that's basically, it's going to equal the range of those 3 numbers divided by 2, so half the range, max minus min over 2. But then you've got to divide by 5 because the times here are 5 times as big as the period. So let's put all that into our formula. Equal sign, we want to take the maximum value of those 3 numbers, subtract off the minimum of those 3 numbers. I'm going to put brackets around that whole quantity, which would be the range. Then I've got to divide the range by 2, max minus min over 2, but I've also got to divide by 5 because that time is for 5 periods. Press enter and I get that number. Let's pull those down and I get these numbers. These are uncertainties, so 1 significant figure is fine. What you want to notice here is the uncertainty isn't increasing or decreasing. There's no obvious pattern. The largest value for the uncertainty is 0.06. We just want a rough estimate of that uncertainty. We've only got 3 trials, so we're expecting that over some of the trials we're going to get too small of a range. And we're better off to kind of overestimate our uncertainties than underestimate our uncertainties, and we also tend to like to choose nice round values. So I'm going to choose 0.05 as a typical uncertainty. And I'm just going to use that for all my periods. So I'm now ready to make a graph. So I've made my columns a little bit narrower. I've changed the view to 75% just so we have more room to put a graph in. So to start off the graph, just highlight all of your data. Once you've done that, go up here to Insert, Insert Chart. And you'll get some kind of wild looking thing here. And this thing called the chart editor should open up right away. If it doesn't open up right away, just double click on your chart and it'll come up. So if we go to Setup here, the first thing we want to do is choose the right type of chart. And what I'd like is a scatter graph, which is right here. I want to notice here that these numbers along the horizontal axis, those are my lengths. Those are my lengths from this column, and that's my independent variable. Those are the x values that I want. That's good. And then I've got every single one of my columns here is another separate y variable. And the only one that I want to plot is the average period here. So what I'm going to do is get rid of the rest of them. So my x-axis, that was okay. I've got the x variable there that I want, the length of the pendulum. But the series here, those are my y values. And there's only one y value that I want, and that's the average period. So I'm going to remove all the other ones, and then I get this graph here. So I'm noticing here that 0, 0 is not on my graph, and I start thinking about a pendulum. Well, a pendulum, if it's got 0 length, it takes 0 time to go 0 length. So we know without any uncertainty that when the length is 0, the average time is also 0. So I'm going to include that as a point on my graph. And so now that point's there. And you can see that this doesn't look like a straight line anymore. It actually looks like a square root function like it's supposed to. So let's double click on here. Bring up the chart editor again. So I've selected my data in the right place. And I'm going to go over here to Customize. And at the top of that, chart style, my chart style seems to be fine. Chart axis and titles, let's put those in. Let's start with our chart title. I'm just going to call it the period of a pendulum. And I also want a horizontal axis title. That's going to be the length of the pendulum. And that's going to be plus or minus 0.1 centimeters. And on the vertical axis, that's where I've got the period or the average period. And that will be in units of seconds. And if you want to include that typical value for the uncertainty in the period, we could write in a plus or minus 0.05 seconds. Okay, so I've got my axes now. Let's continue on I'm going to close up the chart and axis titles. Go on to the series. That's where all your data stuff is. And there's some important things that you can do here. For instance, I don't like these circles. I'd prefer to use X's because they're a little more precise. I would like error bars. And I don't want it as a percent. I want a constant value. That typical value I was just stating of 0.05 seconds. I don't want data labels. I would like a trend line, so I'll click on that. I don't want a linear one. A square root is like x to the 1/2. So it's a power of x. So the type of function I want is a power series. And here where it says label, right now there's no label, but I can put an equation in there. And you'll see I get 0.204x raised to the 0.499. Well, 0.499 is essentially 0.5 or 1/2. So this really is a square root function. The r squared value tends to be important in math, not so important in physics. We tend to discuss these ideas in terms of uncertainties instead. Legend, well, I've only got one curve, so I don't need a legend. My horizontal axis, it's going from 0 to 100, and I'm happy with that. I'm not going to change it. I'm going to write in the values anyways, but that's what I want. Let's do the same thing for the vertical axis. So this time my minimum value, I don't want it to be negative 0.5. I'd like it to just be 0. And 2.5 seems good. I'm done on my vertical axis. Let's go down to grid lines. There's a few important things that you can do here. My major spacing type we're on the horizontal axis. I'd like to, instead of going up by 25 every time, I'd like to step up by 10. So I'm going to step up by 10 instead. And I'd like to have some minor spacing as well. And I'll step up, let's say, by 2. So now I've got a bunch of vertical lines as well. You might choose to make the color of your grid lines a little bit darker so it shows up more. I'm now going to go to the vertical axis and do the same thing. I'm happy going up by 0.5 here. I think that's good. But maybe I'll have 5 steps in between 0 and 0.5. So my minor count, I'm going to go up by 5. So now we've got this going 1.0, 1.1, 1.2, 1.3, etc. So that's a pretty good looking graph. So what I'd like to do now is linearize my data. That is, make a linear graph of my data. So we've got a pendulum, and we know that theoretically the period should be equal to 2 pi times the length over g. So I can write this as 2 pi all over the square root of g times the square root of L. And if I do that, this can be my y variable, square root of L could be my x variable, and this would be a constant that will end up equaling the slope. So if I make my graph of t versus my x variable, which will be square root of L, I should get a straight line, and this slope should be equal to 2 pi all over the square root of g. Alternatively, you could square both sides of this equation and write t squared equals 4 pi squared over g times L, and then you'd make the L your x variable. T squared would be your y variable, and this thing here would be the slope. So when you graphed t squared against L, once again you get a straight line, but it would have a different slope equal to 4 pi squared over g. I'm going to use this method here, but it really doesn't matter. Some people prefer not to work with square roots and prefer to work with squaring. So I'm going to be needing a new column of data. I need my square roots of L. So what I'm going to do is insert a column to the right of the first column, column A. So now I've got a new blank column. This is going to be for the square root of L. And so I need a formula, equal sign, SQRT for square root. And there's my cell with the value. And now I just need to pull this down. And there are all my square roots of those numbers. I need some more decimal places here. So let's add a decimal place. I'll give it 2 decimal places. So now I need to make a chart. I'll just highlight all the data again, insert a chart. My x-axis, I need to add an x-axis, and I'd like it to be this column here with the square root of L. My independent variable, my y variable, is going to be the average period, so I can remove these others. And I'd also like to have a scatter graph again. Let's go to Customize. Horizontally, my variable is the square root of length, and the units there would be the square root of centimeters, so I'll write that as centimeters to the 1/2. My vertical title is going to be the period in seconds, and I can use that 0.05 seconds as my plus minus. Once again, I prefer the X marks. I want some error bars, and this is one of the advantages of the period is I already have the size of my error bars, constant value 0.05. And I do want a trend line. This time it's a linear trend line, and I do want to show the equation. Horizontal axis, I'd like to go from 0 to 10 is fine, what they've done. Vertical axis, I'd like to go from 0 to 2.5 would be fine. And my grid lines, I'm going to step up by 5. I'm going to step by 0.1. That looks better. And on the horizontal axis, I'd like to go up by 1 each time, and I'll step up by 0.2, and that'll look a little bit better. So I've got a y-intercept here, very, very close to the origin, which it should be. It should really be going exactly through the origin. And there's a very quick way to get an estimate of the uncertainty in the slope and the uncertainty in the y-intercept. What you do is you type an equal sign for a function and then LINEST, like so. Put your y values first. So my y values were these average periods right there, comma, put your x values in, which were these square roots, just highlighting those cells. Calculate b. Well, in this case here, I don't want to calculate b. I'm going to, because in a sense I've already done it. I know it's very close to the origin. I know it's supposed to go through the origin. So I'm going to write false here. And so it's going to force the line of best fit to go through the origin. And for verbose here, that's just going to give me a matrix of numbers. And one of the numbers in there will be the uncertainty in the slope. And that's the one that I'm really after. So I'm going to write true there. I want to do these calculations on the data. Press enter. And here's the matrix that I get. So that 0.202, you'll notice that that's the same as here. That's the slope. And the y-intercept, well, we set that to 0, so it's not quite the same as what it was originally. Now, here's the number that's important. So just kind of highlighting here, that first number was the slope. The second number was the y-intercept. The third number here is the uncertainty in slope. And then the fourth number would be the uncertainty in the y-intercept. And these calculations are not using the uncertainties at all. all that's being used here is the fluctuations in the data. They're looking at how far the data is from that line of best fit, and they're using that to make an estimate of the uncertainty in the slope. And this works quite well. Tends to give you small values for the uncertainty in the slope. As you can see in this case here, where the uncertainty, this number here, it's only about 1 in 2,000th the size of the slope itself. So we're getting a very small value here for the uncertainty in the slope. And let's note quickly here, if I change my parameters, if I come up here and I change that false to a true and press enter, now I do get an uncertainty in the y-intercept, and you can see that it's big enough so that our actual y-intercept is within uncertainty, within this number of the origin of 0. And you'll also note here that that y-intercept corresponds to the y-intercept given in the equation here. But let's go back and put it the way we want. Once we've got the slope here and the uncertainty in the slope, so our slope is equal to 0.20, rounding up 0.203 plus or minus 0.001. So the slope ranges anywhere from a minimum value of 0.202 up to a maximum value of 0.204. And we said that the period is given by 2 pi over the square root of g times the square root of L. And this thing here is supposed to equal the slope. So we can set those equal to one another. 0.203 is equal to 2 pi all over the square root of g, and we can solve for g. It's going to equal what? 4 pi squared divided by 0.203 squared. And if you work that out, you should get 958 centimeters per second squared. So that's a little bit low. It should be 981 centimeters per second squared, or 9.81 meters per second squared. What we can do, though, is we can work out what's the minimum value that we could get for g from our data, and what's the maximum value. So the minimum value would be, when we have that 4 pi squared, divided by the largest possible value, which would be that 0.204. And you need to square that. And you get a minimum value of 949 centimeters per second squared. Do the same thing for the maximum, 4 pi squared divided by the 0.202 squared, and you should get 967 centimeters per second squared. So our experimental g value lies between 949 and 967. And 9.81, the accepted value, is outside experimental uncertainty. So then, of course, we need to ask, why is that so? And we start thinking about, well, could there be a systematic error? And maybe you remember when you're measuring the lengths of the pendulum, you weren't measuring to the center of the bob, you were just measuring the length of the string. And then you'd start thinking about, well, if I am consistently measuring the length of the string to be too short, is that going to give me a g value that's too large or too small? And you can kind of test that out. You can say, well, if I rearrange this equation here, I get that the square root of g all over 2 pi is equal to the square root of L all over the period. So if my L value is consistently short, my g value will also be consistently short. So I'm beginning to think that maybe I've identified a systematic error in my experiment. So here's the graph of our data. We use this linear estimate to mathematically work out the uncertainty in the slope. But you'll recall we had another way of finding out the uncertainty of the slope. And that was to draw a maximum and minimum slope line. Now if you do that in this case here, maximum slope line would go up to the top of that error bar, and the minimum slope line would go down at the bottom of that last error bars. And you notice that the two lines go through all the error bars. We're anchoring everything to the origin. But what you notice is the three lines, the trend line, the max line, the minimum line, they're all basically on top of each other. And if that's the case, then you're best off using the linear estimate, LINEST. Do that mathematical test to find out the uncertainty in the slope. If, however, your uncertainties are larger, so let's say that we change the uncertainty in the average period here from 0.05 to 0.2, then it would look something like that, and we'd have our error bars about like that. Now this becomes kind of useful because you can see if, for instance, this point here, you could see that the maximum and min lines are well within the uncertainty bar. But at some other point, it might be such that the data point is right on the edge of a max min line. So it's a little less reliable. So what we're going to do is carry out this process with the max and min line. The points that we're going to use, we're going to anchor to 0, 0 for both the max min line down here. And then this point here is going to be the point 10 and 1.8. This point here is going to be the point 10 and 2.2. So we're back to the data. I'm going to type in min and max. These are going to be where I put the y values for my minimum and maximum slope lines. Now I'm anchoring things to the origin. So when my square root of L, my x value is 0, on the minimum line, the y value will also be 0. And on the maximum line, the y value will be 0. When I get up to this last point, square root of L equal to 10, the bottom of the error bar crossed at y equals 1.8, and the top of the error bar crossed at y equals 2.2. So now what I'm going to do is just highlight all of my data. I'm just going to select all of my data there. And I'm going to insert a chart. And of course I want this to be a scatter graph. My x-axis, I don't want that to be L. I want that to be the square root of L. So I'm going to remove that and add square root of L for my x-axis. And then my series here, I've got a ton of them. I'm going to remove them all. And then I'm going to add a series. I want the average value of the period. Another series is going to be my minimum slope line, and another one's going to be my maximum slope line. So there's my data. What I'd like to do now is go over to Customize and go down to Series, and to my trend line, my average T line, I want stars, I want error bars, and if you'll recall, we changed that from 0.05 to 0.2. And I want to draw the trend line. It's going to be linear, and I want to label it with an equation. And then for the minimum, come back up here, for the minimum line, okay, color red, that's fine. Would also like a trend line. It's going to be linear, and I do want to show the equation. Now let's go back up here to my maximum slope line. So I do want a trend line, and I do want an equation. So now we can see that the maximum slope is 0.22, the minimum slope is 0.18, and our uncertainty in the slope would be max minus min over 2. It would be 0.22 minus 0.18 over 2. Just writing that down, the uncertainty in the slope would be equal to the max slope minus the min slope divided by 2. So in this case, it was 0.22 minus 0.18 all over 2, which is 0.04 over 2, which is 0.02. So we're going to have a nice visual picture with our graph. You'll be able to see that the minimum and maximum slope lines go through all the origin. You'll be able to see if it's anchored through the origin. So it gives you more information than if you just used the linear estimate test, LINEST.
And that's all for today, folks. Thank you very much.